Hey, what is up everybody, and welcome to the 36th installment of our little series on Vertex Operator algebras. Today, we finally get to study those eponymous beasties. So, let's get started. For a little context, you might recall that we've been studying the affine Lie algebra associated to SL2, and a specific version of it twisted by conjugation by the matrix sigma 1. This involutive automorphism acts on our Chevalley basis by sending the diagonal element out to minus itself and flipping the roots. This means that those affine elements based on sigma are odd under the involution, which means that they belong to the half-integral graded subspaces. So for our purposes today, we'll be starting from the Heisenberg subalgebra of the sigma 1 twisted affine algebra we constructed a while back, h hat z plus 1/2. This subalgebra is spanned by the central charge C and those elements based on the sigma matrix sigma. For a bit of operator notation, call sigma of n the affine endomorphism associated to sigma t to the n. We can then present the familiar commutation relations, which of course reduce to the central term. Note that the standard inner product, basically the killing form on SL2, gives 2 in this case. Now, h hat z plus 1/2 has a one-dimensional center spanned by the central element C. So, of course, the subalgebra is Heisenberg, and as you might remember, by the Stone-von Neumann theorem, we have an irreducible representation for it in terms of the symmetric tensor algebra of the negatively graded subspace of h hat z plus 1/2. On this module, C acts as the identity operator, which we take as definition at this point. And of course, D is the degree operator. We want to show that the endomorphisms of this Heisenberg module have elements associated to the root vectors in the affine Lie algebra. Those operators we now call sigma plus or minus of n. From there, we can go on to argue for the full SL2 hat sigma 1, that is twisted affine module. Anyway, that's the strategy we're going to employ moving forward. To start, we'll set up the equations for what these endomorphisms of M1 must look like. To simplify things, let's just call that module V, and recall that C is the identity map on V. Similarly, the operators sigma of n are the endomorphisms of V, and they satisfy the equations given here. So let's consider some generic elements, alpha and beta, in end of V. The idea here is that H, the Cartan subalgebra of SL2, may only be one-dimensional, but we have our eye to the future where H might be multi-dimensional, which explains, all the added complications. Now, by analogy with the previous expressions, we have commutators for alpha and beta written in terms of their inner product. And once again, we point out that notationally, alpha of m is not a formal series, but rather a specific endomorphism, which, for example, may be the operator of degree m. Perhaps one in SL2. Now, as stated, our aim is to find the endomorphisms associated to the affine algebra members sigma plus minus. So, to do this most efficiently, let's switch to the discussion in terms of formal series. The notation is mixed now, but things should be clear from context. The commutator of endomorphism sigma of m with either of the formal series sigma plus or minus is given as follows. Here, we're following FLM with the observation that the commutation relations can be compactly written in terms of the inner products of sigma with plus or minus itself. There's not a good a priori reason at this point why we should write it this way, why this notation exists, but hey, let's just take it as notation and move on at this point. Okay, so let's go back to the endomorphisms of V. Remember that we haven't shown that V is an affine SL2 module yet. All we can do is hope that the affine operators sigma plus or minus are actually endomorphisms of V that satisfy the algebraic relationships that are identical to those of the affine Lie algebra SL2. To check in on that possibility, let's start by defining a general endomorphism U indexed by some alpha in H, the Cartan subalgebra. We can then construct the formal series big U of alpha and Z as the formal sum in the usual way. We then demand an algebra behavior of big U, namely that it satisfy the commutation relations familiar from the roots of the affine Lie algebra, including the degree derivation condition. If such a big U exists with alpha equal to sigma, we could identify it with the endomorphism series sigma plus or minus of Z, and be well on our way to constructing our affine SL2 module. So let's solve those algebraic equations for big U. You know that a problem is challenging when it starts with the words, "Consider this seemingly irrelevant thing." And so we do. E plus or minus, formal series of endomorphisms of V. These beasts are actually exponentials of the various half-integral graded endomorphisms, except E plus contains only the positive indices n plus 1/2, and E minus contains only the negative indices, minus quantity n plus 1/2. This is not unlike splitting Fourier series into positive and negative frequency components. And we do this here because the endomorphisms alpha of m all commute with one another if m and n are both positive or both negative. Now, we prove a little claim about these beasts E plus or minus. It's a claim in 4 parts. First, alpha equals 0 means that E plus or minus are the identity operators. Second, E plus or minus of alpha plus beta split into 2 operators, E of alpha times E of beta. Third, E of minus alpha equals limit of E of alpha, where we take Z to the 1/2 to minus Z to the 1/2. Fourth, that these operators satisfy the degree derivation condition in the usual way. Proof. The proof of part 1 is simply a matter of the definition of the exponential. To prove 2, we need the fact that the endomorphisms whose degrees are both positive or both negative commute. For then the result is but a simple application of the Baker-Campbell-Hausdorff formula. To prove 3, we need only appeal to definitions, which means we now examine part 4. To prove 4, let us examine the endomorphism series A, which is essentially the argument of the exponential. It's clear here that the commutator with the degree operator picks out n from alpha of n, which is equivalent to the application of big D degree operator acting on the formal variable Z. And so we have the following identity. Now, notice that A itself commutes with that result. So, as per usual in these kinds of situations, we find that the degree derivation on some suitably well-defined function f of A amounts to the derivation of D with A times the derivative of f of A. Though in particular, this applies rather simply to the case of the exponential. This, of course, implies the results for E plus or minus that we were after, and so we're done. Now, we can apply this same idea to the study of the more generic commutators with E plus or minus of alpha and Z. For some generic h of m in the Heisenberg subalgebra, we compute the commutator with E plus or minus, which essentially reduces to the commutator of h with A, which vanishes, of course, for m greater than 0 with E plus. Again, using the fact that positive index operators commute in the Heisenberg algebra. This is also true for negative m and E minus. So we are left with opposing signs, and there we simply apply the commutation relations discussed earlier to compute h with A and E plus or minus. So it would seem that E plus or minus each solve half of our problem. The problem of solving those algebraic equations. So it's natural to ask if we might try to combine them together. The naive choice of simply adding them together fails, and it fails because E minus actually isn't well defined as an operator on V. V, you might recall, as part of the assumptions of the Stone-von Neumann theorem, must have a highest non-trivial grading beyond which each homogeneous space of higher degree is trivial. In short, we are dealing with representations of highest weight, finite highest weight. So, do you know what's well defined in this context? The product E minus times E plus, of course, where E plus is on the right and gets to act on V first. To connect with our discussion of Fock spaces in quantum mechanics earlier on the quantum harmonic oscillator, you might consider E plus to be the annihilation operators A, and E minus to be the creation operators A dagger. Our expectation from the outset is that all of the relevant states of those are highest weight, and therefore are annihilated, or mapped to zero, in other words, by some finite polynomial in annihilation operators of sufficiently high degree. Awesome! So now we're at the point where we can define the twisted vertex operator big X of alpha and z, defined as the product of E minus times E plus over some normalization constant. It's a convention that we choose the inner product of alpha with itself to be an integer. And since we'll be doing a lot of work with lattices in the future, I hope this serves as a bit of a preview as to why. But anyway, that's our show. Next time, we'll demonstrate that the twisted vertex operator shown here is the unique solution to those algebraic equations, or rather, it's unique up to a scalar multiple. Thank you so much for watching. See you next time.
I've been feeling so small. Watch the clock ticking off the wall. But tonight I'm letting it go. Spend my coin for sure. I'm gonna be myself, or I could be someone else. No one's stopping me now. I'm gonna skip my breaks, I'm gonna make mistakes. I just wanna feel alive. It's just what I do when I'm out, so try not to hold me down. Feel alive when I'm in this town. Look at those beautiful stars. I wanna drive a faster car. Nothing can break me, no, nothing can break me. Lay my troubles to rest. Blow the smoke through my cigarette. City lights looking fine, and I know this is my time now. I'm gonna be myself, or I could be someone else. No one's stopping me now. I'm gonna skip my breaks, I'm gonna make mistakes. I just wanna feel alive. It's just what I do when I'm out, so try not to hold me down. Feel alive when I'm in this town. Look at those beautiful stars. I wanna drive a faster car. Nothing can break me, no, nothing can break me. Look at those beautiful stars. I wanna drive a faster car. I'm gonna be myself, I'm gonna be someone else. I'm gonna be myself, I'm gonna be someone else. I'm gonna skip my breaks, I'm gonna make mistakes. I'm gonna skip my breaks, I'm gonna make mistakes. I'm gonna skip my breaks, I'm gonna make mistakes. I'm gonna skip my breaks, I'm gonna make mistakes. Try not to hold me down. Feel alive when I'm in this town. Look at those beautiful stars. I wanna drive a faster car. Nothing can break me, no, nothing can break me. Look at those beautiful stars. I wanna drive a faster car.